Hello. Is it? Yep, it started. Okay. So today is the last chapter of shearing stress. Okay, the last. And some will say, oh, thank God. Okay. So this is the last chapter. Okay. And we're going to focus on unsymmetric loading of thin wall members. Okay, unsymmetric loading now. So this is, if you're going to read the textbook, okay, it's on chapter 6.9. Okay. So now let me tell you what is symmetry loading first. Okay. So what you see over here, okay, what you see in this diagram, by the way, this diagram is on Avenue to Learn. Okay, you should go and download them. Okay, don't draw them. Okay. So this is the condition. Okay, condition of symmetrical loading. Okay, so what you are seeing below. So if I were to sketch out the transformation of what you see down here, so this is my x, this will be my y, and this direction will be my z. Okay, so what you see over here is the structure. Okay, so with applied force P, right, and the P is in line to the centroid. Okay, I repeat again, the P is aligned to the centroid, and the centroid about the z-axis. Okay, is aligned. So the for this case, the structure, right, the structure will bend in the xy plane. Okay, only. So what do I mean? Only in the xy plane. So if this is our xy plane, okay, so this is our, where I'm shading now is my xy plane. So I'm going to sketch how this structure will deform. Okay, I'm going to do a rough sketch. So the structure will deform something like this. Okay, so the structure will deform something like this. Right, so this is how the structure will deform. Okay, so if you look on the other diagram, 6.4, as what it states out there. Okay, so deformation restructure. Okay, so deformation of the structure okay is only by bending oh, you guys will probably want to see this. Oh, sorry, only by bending and the deformation or deflection will occur on the xy plane only. Okay, so there's two general formula that we're going to apply to analyze the structure over here. Okay, so the first formula, as you all know, okay, if we have force at P, okay, at P, force at P at the end of the cantilever beam, so the formula we're going to apply is stress X, right, is equal to minus my, okay, my over, sorry, it's not my, mz, because the moment is about z, over izz and multiply by y, right? And then the other formula that we're going to apply, okay, to calculate the shearing stress, which you guys are really, really good at it already. So we know that shear xy, right, is equal to Vy over Izz Okay, first moment of area about a z-axis divided by t, right? So you guys are aware, okay? So I'll call this equation number 1, and this is my equation number 2. Okay, so we are clear about this. Okay, now next I'm going to show you a condition where it's classified under unsymmetrical bending. I repeat again, it's classified under unsymmetrical bending. So I'm going to write down here condition of unsymmetrical bending. Okay, so condition of unsymmetrical loading, not bending, sorry, unsymmetrical loading. So when that's the case, okay, I'm going to copy some figures. Again, I said again, you all will have these figures down here. Okay, copy. Okay, so this is the condition of unsymmetrical bending. Let me get the other cross-sectional view so you can see better. Okay, but before I do that, let me go back to this slide, this figure over here. Okay, so as you can see, what we are seeing down here is this based on transformation. This is our y, this is our z. Okay, this is rotation about x. Okay, so just to recap what we learned last week and will help you in your homework 7 is the shear flow. Okay, we know that the shear flow is controlled by the what? By the web, right? The shear flow direction. Okay, shear flow direction is controlled by the web. Okay, by the web. So we know that the shear flow will be coming down this way. Okay, so this is our Q, right? It's controlled by the web. Okay, so this is our web. And then we have, okay, so as you can see over here, we have one start point. So above the neutral axis, as you can see, is a box beam, right? Remember that? And below that is a white flange. Okay, so down here the Q split into 2. Okay, and over here you have 2 endpoints. So endpoint number 1, endpoint number 2. Okay, so at the top, the analysis, just to recap, is a box beam. At the bottom, okay, is a white flange. Just to recap with you guys. Okay, now let's go to condition of unsymmetrical loading now. Okay, so what you realize from here now, okay, the difference is this. Okay, one of the difference. Okay, one of the difference is this. So if this is our centroid now, this structure shows some deformation already, right? So if this is initially this is our C, right? And the applied force is applied a certain distance away from the centroid. Okay, a certain distance away from centroid. Okay, so when that is the case, okay, we are going to have issue. Okay, when that's the case, you can issue. So as you can see, how the structure is deformed. Okay, as you can see how the structure is deformed, the structure will bend. Okay, so if we were to draw our transformation, so transformation did not change. Okay, so this is our Z. So structure will bend. Okay, the structure will bend in the XY plane. Okay. Now, because of the unsymmetrical loading, okay, where the P is offset away from the centroid, what we are going to have and a twist about the x-axis. Okay, so on, oh, I got this wrong. I do apologize. So this is my y. This is my x. So when that's the case, right, you are going to get a twist in the what? You're going to see a twist along the x-axis. Okay, so you're not just going to see bending. You're going to see a twist. Okay, so why, the question now is, why do we get a twist? Okay, why do we get a twist now? Okay, so now actually this diagram is not a very good representation because the V has to be offset. Okay, so now let's say now the V, okay, I'll leave it. Okay, let's say there's no we're not going to consider the offset down here. It also works because of the strength of structure. Now, question for you guys: which part of this structure, okay, view from this orientation, okay, which part of this structure view from this orientation? So this orientation that I have, so this is my Y, Z, rotation about X. Question for all of you, okay? So at this line that I'm going to draw now, okay, at this line I'm going to draw now. I'm going to draw a line. Yeah, I'm going to draw a line vertically down. Right? Can you tell me which side is stiffer? Stiff means more rigid. Which side is more rigid? The left-hand side or the right-hand side? Can anyone tell me which is more? So which side is more rigid? Anyone, please?
Would the left-hand side be more rigid?
You got it there. Okay. So the left-hand side is more rigid. Any idea why? You're right. But why? So right-hand side is less rigid. Any idea why?
Is that's where the web is?
Okay.
Is that because that's where the web is, like the vertical orientation?
Yeah. So on the left-hand side, you have a what? You have a web. Yes or no? To enforce. The right-hand side, you have no web. So when this is the case, what will happen? The structure will want to what? Will want to twist, right? The structure will have a tendency to twist, right? So when that's the case, the structure will have a tendency to twist, right? We don't see that up here. We don't see that in over here, right? Because both sides has a web, right? And a symmetry, right? Left-hand side and right-hand side. Yeah, you draw a vertical line is the same. For this case, it's not. Okay, the left-hand side has a web. The right-hand side has no web. That is why it is less stiff or less rigid on the right-hand side. Okay, so like a typical engineer, okay, like a typical engineer, okay, how are we going to apply, okay, the shear stress is equal to VQ over IT. Okay, so what do I mean like typical engineers? Okay, we don't want to so-called put in a new formula. In fact, there are other formulas that you can use to approximate the shear stress when you have a twist. Okay, there are other formulas around, but we don't do that. Okay, I say no. We don't do that. We still want to force this formula. So this formula that I've written down, this formula that we've written down, okay, no twisting is allowed. Okay, so it does no twisting. If it twists, this formula will not work. Okay, so no twisting. So what we're going to do now is we're going to you heard our term, right? Square hole, round peg, yes or no? So if your hole is square, right? Your hole is square, you have your round peg, you have to force it through, okay? That is what generally engineers are all about, okay? But we have to be really cautious about this. We have to really cautious. So how about do we do that? Okay, how about do we do that? So I'm going to copy another set of diagrams, okay? How about, so how to apply, okay, how to apply the shear stress is going to VQ over IT, or the shear flow is VQ over I, even with twisting, even with twist, or what we call unsymmetrical, okay, or unsymmetrical loading. Okay, I'll tell you the good news. Okay, I'll tell you guys the good news first. The good news is we still apply the 4 rules that we learned. I repeat again, we still apply the what? The 4 rules that we have learned. The 4 rules still stand. Okay, we still apply how we design the shear flow. Okay, still the same thing. Okay, but now there is one slight difference, and this difference is not ridiculous. Okay, it's not ridiculous. So I'll get you the image, and you can see better. Okay, so this is the image I'm going to use. Okay, I want you to hear me out. Okay. Now, so what is going on now? Okay, what's going on before? Okay, what's going on before? What is going on before is the structure wants to twist. Okay, so let me draw my transformation first. Okay, X, Y, and this is Z. Okay, so the structure, okay, originally wants to twist. Okay, so it's going to twist in this way, right? So I'll say this is the twist about the x-axis. Okay, you want to twist. So to prevent it from twisting, okay, to prevent this from twisting, we are artificially, okay, I repeat again, we are artificially putting a block over here. Can you see what I'm drawing now? This is an artificial block. This is actually not there. Okay, this is actually not there. But in our analysis, we're gonna create a block like this, right? And then we're gonna put a force P, a certain distance away from the structure known as E. Okay, you see this term E, right? So what this does, okay, is based on Newton's third law, action equal to reaction, same in magnitude but different what? In direction, right? So this is induced, right? This is induced by the counter. Okay, so this is the counter twist. Okay, this is known as the counter